What's going on, everybody? This is your pal, Professor Withrow, here with the first of what will no doubt be many online lectures here for our trigonometry class at ECA in the spring semester of 2020. I hope you all are well. Let's begin. We've been taking a look at some trigonometric identities long before this particular class, and right before we went into spring break, we were taking a look at the process of verifying some additional trigonometric identities. We were using some identities that we were already aware of, namely some reciprocal identities that we've seen really from the start of the semester here. That sine is the reciprocal of cosecant, and cosecant is the reciprocal of sine. Reciprocal, by the way, does not mean that they're inverse of one another. There is an inverse sine and there's an inverse cosecant. The difference is whether or not these ratios are reciprocals of one another. When you're dealing with an inverse trig function, that's different than reciprocal. That deals with whether or not you're going from an angle to a ratio or a ratio to an angle. So reciprocal does not mean inverse. So when we're dealing here with some of our identities, we start here with the reciprocal ones, of which sine and cosecant have that relationship. In addition to cosine and secant, those also have that reciprocal relationship. And lastly, you guessed it, it's tangent and cotangent that also have that same relationship. In addition, we have our family of what we call quotient identities here, where if you know sine and cosine, you can find out what tangent is, and you can find out what cotangent is just by reversing the ratio. We also have two other classes of identities to work with here. These are the Pythagorean identities, the ones that ultimately stem from our old pal a squared plus b squared equals c squared. We've seen it in this form. We've sometimes called it Efron's theorem. Hello, Efron. It also appears in two other forms that we've seen before as well. Tangent squared x plus 1 equals secant squared x, and also cotangent squared x plus 1 is equal to cosecant squared x. So we'll be looking for secant squareds and tangent squareds and cotangent squareds and cosecant squareds to see if you need to make these kinds of transitions as we're proving some additional trigonometric identities as we go forward here. Lastly, there are some cofunction identities here. This deals with the relationship between sine and cosine. Remember, sine is the opposite over hypotenuse, and cosine is the adjacent over the hypotenuse. And so when we're dealing with the sine of one of those angles, we're getting the cosine of the other angle on the triangle, and vice versa here. When we're dealing with the cosine of one of those angles, we're dealing with the sine of one of those angles as well. These cofunction identities also exist between tangent and cotangent, and also between secant and cosecant. And so these are the kinds of tools that we're going to be using with as we derive some additional identities as time goes on. This is what's kind of cool about trigonometry, in that it's like you start off with a set of tools in your tool shed, and part of what you are able to do is eventually create some additional tools that are all the more useful as well. But it's like you're using some tools to make bigger tools, and so you're building this arsenal of tools that are available to you. So it's pretty cool to be able to do this. But first, before we do this, let's take some time for ourselves here. This is some time, we've done this in class quite a bit here. Empty your mind of thoughts and take some time to focus on the now, and to essentially see if you can feel that your hands are alive, your feet are alive, your knees are alive, all of those things here. But do those things to help you clear your mind and focus on your breathing. Let's take some time now to begin. Whoops, that's not working right. I'm still figuring this system out here. So let's start here. First of all, what is an identity? Let's take a look at what exactly that is here. Well, we've got this simple equation here, and this equation is something that you can probably automatically think of some ways in which you can solve this for x. If you subtract 1 from both sides, you get 2x equals 4, and if you divide both sides by 2, you get x equals 2. So the point here is that this equation has a specific solution. Not every possible number, every possible value for x is a solution to this equation. So this has a specific solution. It is not an identity. So if it's only true for a single value of x, then it's not an identity here. But this equation, if, for example, we go through the process of solving this and we discover that exactly the same expression is on one side of the equation versus another, then, we'll eventually subtract off 4 from both sides. We'll get 2x equals 2x. We'll perhaps subtract 2x from both sides. We'll get 0 equals 0. Well, how often does 0 equal 0? The answer is all the time, no matter what the value is of x. And so this is true for all values of x. So equations that are true for all values of all variables are called identities. So the thing is that when we're trying to verify an identity here, I'm assuming that this is true. This is the same as this for all values of theta. And in order to prove that, I'm stating that this is equals here, but I'm stating this as a proposition. I'm actually not sure that this is true. That's why there's a question mark sitting above here. Now here's the thing. Since I'm not certain that this is true, I cannot do any of the things that we do algebraically based on the assumption that we have two things equal to each other. Look at all these things here that we've been using all this time here. Addition property of equality. That's where you add something to both sides of an equation. You're assuming equality in order to be able to do that. We cannot assume that here. Same thing with subtracting something from both sides of an equation, or multiplying or dividing something to both sides of an equation. We cannot do that because we have not demonstrated yet that these two things are equal. So we cannot assume that these things are equal, so we can't use any of those tools. So what do we have to do? We're not allowed to add or subtract anything from both sides or multiply or divide both sides by anything. So we're stuck with working each side by itself. We can simplify what's going on over here and hope that we can get to something that looks exactly like the other side here, or vice versa. We could start here and try to get something that looks exactly like this, but we can't work both sides of the equation at the same time. Okay, so let's do that. Usually it's a good idea to begin with the side of the equation that's more complex. I found that that tends to be a little easier than to work with the side that's less complex. So, all right, this is the side that's more complex here, and you can take a look at some of these things here. Boy, that's that familiar secant squared. When I look at that, that could, secant squared minus 1, I believe, is tangent squared. So we can make that substitution here, tangent squared over secant squared. Think of some things that we can do in order to simplify that. We eventually want to get to sine squared. Well, tangent squared is equal to sine over cosine, and dividing by secant squared, that's secant squared is equal to the reciprocal of cosine squared. So let's break these things up into sines and cosines, and let's just see what we've got here. Well, we actually can do something similar to that, in that if we multiply top and bottom here by cosine, secant and cosine are reciprocals of one another, which means that if I take secant and multiply it by cosine, that's just going to turn to 1. And so let's see what happens here on the top when I do that. We've got just 1 on the bottom here. Tangent squared times cosine squared. What is that? Well, let's split tangent now into sine squared over cosine squared. Ooh, we now have something that can cancel with this cosine squared, and we're left with sine squared here. We have now, using none of the assumptions of equality, we've only been working with one side of the equation, and we've been able to manipulate it so that this can be shown to be the same thing as this, always, always, always. So we have proven this identity to be true. So do this one yourself to see how how well you do with this. Take some time for that now. Welcome back. This is a good example of a problem that makes use of multiple different identities in order to solve it appropriately. If we take a look at what happened here on the top, the numerator that is, sine squared plus cosine squared very easily becomes 1, and the fact that cosine and secant are reciprocals of one another mean that those two are going to cancel out with each other as well, meaning that we get 1 here. We have proven this identity. Hopefully that was straightforward here. Well, here's another example here, and again, we are proposing that the equality is true here. We're proposing that these two things are equal, seeing that the stuff on the right-hand side is more complex than the stuff on the left. I'm going to start with the stuff on the right here. So we've got 1 over 1 minus sine alpha 1 plus sine alpha. Boy, we've got these two denominators here. How is it that we usually add things that involve different fractions? Well, we have to get a common denominator. We have to make it so that the denominators are the same so that we can add them together here. So how exactly can we do that? Well, if I take a look at 1 minus sine alpha and 1 plus sine alpha, if I multiply this first fraction, top and bottom, by 1 plus sine alpha, then, and do the same thing here, well, something similar to it, with this second fraction, where I multiply this second fraction top and bottom, not by 1 plus sine alpha, but by 1 minus sine alpha, that'll make it so that my two denominators are the same here, 1 minus sine alpha times 1 plus sine alpha. That'll allow me to combine them into a single fraction here, and I just add the stuff here that's on top. Okay, so 1 times, okay, that's not going to do anything. So I've got 1 plus sine alpha plus 1 minus sine alpha. So that's what exists here on top. Okay, so what's going to happen here on top? I've got plus sine alpha and minus sine alpha. Those two things are going to cancel, leaving behind just 2 over, 1 minus sine squared alpha. 1 minus sine squared alpha. This is another form of basically Efron's theorem here. Sine squared plus cosine squared equals 1. Well, if that's the case, then 1 minus sine squared is going to be cosine squared. So this simplifies now to 2 over cosine squared, which, let's see, how can I get it into this form? Oh yeah, secant and cosine are reciprocals to one another, so 2 over cosine squared alpha is the same thing as 2 times secant squared alpha. So we've proven this identity here once again, so that you can see that these two things are equal. Not just equal for this value of alpha, they are equal always, always, always for all values of alpha. This is an identity. So here's another example here for you to do. Take some time for this. It's very similar to the previous problem that we were doing before. See if you can get that common denominator and combine those fractions together to see if you can get something similar to 2 cosecant squared beta. We're working with beta now instead of alpha. Take some time for that. Welcome back. This is a problem that's very similar to the one that we did together here. If we take a look at this, we are combining these two fractions together. To do that, we get those denominators to be the same by multiplying the first fraction by 1 plus cosine beta and the second fraction by 1 minus cosine beta. That gives us two fractions with the same denominator, and as we add those together, those cosine betas are going to cancel out to just become a 2 on top, and then 1 plus cosine beta and 1 minus cosine beta, those multiply out to give us 1 minus cosine squared beta, which from our Pythagorean identity becomes just sine squared beta in the denominator here. This fraction has become significantly more simple. And then sine squared beta is just the reciprocal of cosecant beta, and so we can make it so we're, instead of dividing by sine squared, we're multiplying by cosecant squared, and the identity is proven. Here's another example here. We've got two things being multiplied together to give us, we think, negative tangent of x. So here I'm going to be, just like before, I'm going to be starting on the left-hand side here since it's more complex. I'm going to start with this. Tangent squared x plus 1 times cosine squared x minus 1. Well, what are some things I can do with that? Well, tangent squared x plus 1 from one of our identities is just secant squared x. And interestingly enough, secant squared and cosine squared, those two things are reciprocals of one another. So if I multiply this, if I distribute this secant squared x to both of these terms here, in the first instance, it's just going to cancel everything out here, and this just first term is going to just become 1. So what I'm going to get here now is 1, secant squared times cosine squared is just 1, and then secant squared x times 1, well, that's secant squared x. So I've just got 1 minus secant squared x here, and once again, I'm reminded of one of our Pythagorean identities here, that connects secant squared x with tangent squared x, so I think we're getting pretty close to a solution here. 1 minus secant squared x, well, I have to factor out a minus sign here so that I can get secant squared x minus 1. I don't know how much we've talked about this before in class, but let me use my pen here as best I can as I do this. This is a new tool here that I've been working with here as well. If I've got a negative sign that I'm going to distribute to two terms here, x minus 2, and I distribute that negative sign to both of these terms here, then I'm going to get negative x plus 2. And since there's a plus sign in between these two things, I can switch them around so that I get 2 minus x. So hopefully you can see here that by multiplying something by a negative 1, if I've got two things that are being subtracted one from the other, I can make it so that I reverse the order of one being subtracted from the other. X minus 2 becomes 2 minus x. I can also go in the other direction here. So if I go y minus x, and in this case I factor out a minus sign here, whoops, still figuring this out. If I factor out a minus sign from this expression here, I have to make this value of this term here for y now a negative y, and if I'm factoring out a negative sign from negative x, that's going to become positive x. So if you're not convinced of this, then let's go back in reverse by distributing this negative sign here. A negative times a negative y, that's just going to be a positive y. Okay, so we're good there. Then we have a negative times x. Well, that's just negative x here. So what we did is the distributive property in reverse here. By factoring out this negative sign here, that reversed the signs of each one of these terms. And notice that means that if we reverse these two terms here, I can get this just x minus y here. So by factoring out a negative sign, or by multiplying an expression by a negative sign, I can reverse the order of two subtracted terms here. And that's exactly what's happening over here. In going from 1 minus secant squared, I can make this a secant squared minus 1 by simply factoring out this negative sign here. That allows me to make this transition here, secant squared x minus 1 from one of our Pythagorean identities. That's just tangent squared x. And so we have our result here, negative tangent squared of x. And our identity here, well, I've got all my jumbled stuff in front of it here, but we have essentially just proven this identity to be true. All right, so do this problem, very, very similar to the one that we just did a moment ago. Take some time for this. Welcome back. This is a problem, like I said, very similar to the one that we did before here. This is an example of multiple trigonometric identities being used once again here. Hopefully this was fairly straightforward in that you could see that you can get a 1 minus sine squared here pretty easily by factoring out a -1. That 1 minus sine squared then becomes a cosine squared down here. And by distributing that cosine squared, this secant squared minus 1 becomes 1 minus cosine squared. You could probably also do something where you transition secant squared minus 1 into some form of tangent squared. Tangent squared times cosine squared is going to be sine squared as well. So you're going to get the same answer using multiple different pathways. But 1 minus cosine squared is our all too familiar sine squared here. So this will be 1. This is a negative sine squared. We've proven our identity. Here's another example here. Tangent x plus cotangent x is equal to secant x cosecant x. This is kind of an interesting one here. So this is a little bit complex. It's hard to tell which one of these sides is more complex to figure out where to start. But when you see something that's really this complex, it's oftentimes just a good idea to break things down into sines and cosines. Then it becomes clear what things can cancel and what things cannot. So breaking things down into sines and cosines, and you can do that for all of the trig functions, makes it so that you've really broken things down to its bare bones pieces. And in this case, if we start with the left-hand side, we've got tangent x and cotangent x. Those break down to sine over cosine plus cosine over sine. And so we now have the task of combining these two fractions together once again. And the process is very similar to before in that we want to get a common denominator here. That means multiplying top and bottom here by sine of x and top and bottom here by cosine of x. So you can see that's what we do here next. Sine x cosine x is going to be our common denominator that we use in order to add these things together. And guess what we're going to see on top? Our familiar sine squared plus cosine squared, which is simply equal to 1. 1 over sine x cosine x. Well, if I break that up into 1 over sine x times 1 over cosine x, what's 1 over sine x? Well, that's cosecant x. What's 1 over cosine x? That's just secant x. So you can see here we've gotten to this point where we have proven this to be true, and so, we've gotten ourselves to go from this point here. Tangent x plus cotangent x is the same thing as secant x times cosecant x. So here's an example of something that's actually very similar to it. I think I've made a mistake here, and that this is exactly the same as the one before. Actually, I'm going to have you do this one here next. Cosecant x minus sine of x is equal to cosine x times cotangent of x. Take some time for that. Welcome back. This is another good example of the value of breaking things down into sines and cosines here. You can see that on the left-hand side here, as we started with cosecant minus sine, you can see here that we broke cosecant down to 1 over sine x, and then sine of x, we actually took the step here as well of making it so that we had a common denominator here by taking sine x over 1, that's what this is, sine x over 1, and multiplying top and bottom by another sine x. So we have sine x in the denominator now. That's going to be useful in a moment. But on top we have not one sine x, but now two sine x's multiplied together. So we can add these two things together to get 1 minus sine squared x all over sine x. That becomes our cosine squared x over sine x. And we can pull out a cosine over here. We can see that that's part of what we're shooting for here is that cosine. And if we pull that cosine out in front here, we're going to be left with cosine over sine. That's just cotangent. And so the identity is proven. Here's another example here. And again, this is the kind of thing where I think that it's usually a good idea to break things down into sines and cosines in an effort to really see what you've got here. And so secant plus tangent x, if we break that down, secant x becomes 1 over cosine x. Tangent x becomes sine over cosine x. Interesting. We already have our common denominator, so it's going to be pretty straightforward to add those two together. 1 plus sine of x over cosine x. Interesting. So let's take a look at what we've got here. Excuse me, what we've got on the other side over here. 1 minus sine x sitting on the denominator and cosine of x sitting in the numerator here. How are we going to make this traverse here? Well, if I multiply top and bottom here by cosine, then I'll be able to get a cosine squared down here. And that's going to be real helpful because that'll allow me to make the jump to a 1 minus sine squared, which gets me closer to this. So the bottom line here is I'm having to go from cosine to sine by using a Pythagorean identity. And I've got to get a cosine squared x in order to make that transition here. So this is the point here. Going from cosine squared x to 1 minus sine squared x is really where we want to go. Because 1 minus sine x is equal to 1 minus sine squared x is equal to 1 plus sine x times 1 minus sine x. And that 1 plus sine x is going to cancel here with this 1 plus sine x factor here on top. Here's what I mean. We're going to factor this out into these two factors here. Notice these two are the same thing, leaving behind just this here, cosine over 1 minus sine here. So how did we approach this? We got to this point here where we said 1 plus sine x all over cosine x. And I looked here at the end and noticed that we have to traverse this. We have to go from it being a cosine x in the denominator to being some expression that involves sine x here in the denominator. So I'm thinking that I need to eventually go from cosine squared to 1 minus sine squared. So I want to get a cosine squared down here so I can make that jump using Efron's theorem. So to get myself here first to cosine squared in the denominator, I'm going to multiply top and bottom here by cosine x, and that'll give me what I want here. So cosine squared of x will be 1 minus sine squared x. Hey, I'm getting closer here because I've got a sine x now in the denominator, and I can factor this out into something, two factors, one of which will cancel out with what's on the numerator here. So that'll leave behind just a cosine x over 1 minus sine x, and that proves the identity. Here's another example here. Cotangent squared over 1 plus cosecant squared is equal to 1 minus sine theta over sine theta. Here again, I think it's a good idea to break things down into well, here again, I think it's a Well, here's one thing that I notice about this. Cotangent squared theta and cosecant squared theta. Boy, this looks an awful lot like our relationship between cotangent squared and cosecant squared. That's one of our Pythagorean identities. So if I can get this close to a 1 minus cosecant squared, then I can have something that's going to become cotangent squared theta, which will actually cancel out with what I've got up here in the numerator. Here's what I mean. If I start off with this and I multiply top and bottom here by 1 minus cosecant theta, then on the top I'm going to get cotangent squared theta times 1 minus cosecant theta. That's the thing I'm multiplying top and bottom by. So when I multiply the top by this, I just get cotangent squared theta times this. But on the bottom, I multiply 1 minus cosecant theta times 1 plus cosecant theta, and I get this 1 minus cosecant squared theta. Well, that's going to be really useful here because 1 minus cosecant squared theta is negative cotangent squared theta. That can cancel out with this, leaving behind just 1 minus cosecant theta over negative 1. Well, that's a negative 1 here that can just as much be out here, or it can be up here on the fraction, so I can just as easily have a negative sign out front here that I can distribute to both of these terms here, giving me cosecant theta minus 1. Okay, so how do I transverse this from this to this? Well, let's break this down here now from cosecant theta to 1 over sine theta, and let's see if I can get a common denominator here to make this into a singular fraction. Well, let's make it so that I have a sine theta over sine theta here. I can convert that 1 into that, and guess what? I've got our solution here at hand. 1 minus sine theta all over sine theta. That proves our identity to be true. Alright, so try this one by yourself here as well. Tangent squared theta, 1 plus secant theta. Boy, I think I recall some kind of a Pythagorean identity that shows a relationship between secant squared theta and tangent squared theta. See if you can make use of that as we are working on this problem together, but on our own. Welcome back. This is another example of making use of a relationship between, in this case, tangent and secant squared, tangent squared and secant squared, to be able to simplify this problem in a way that allows for things to be highly simplified here from secant, from this very, very complex fraction to just secant squared, secant theta minus 1, which if we convert things just down to sines and cosines, in this case just cosines, we can simplify it all the more, and our identity is proven. Okay, these things just get more and more complex. We just get a chance to do more and more of these. Here's our next one here. Notice I've got tangent, not squared here, but tangent to the fourth x is equal to tangent squared x secant squared x minus tangent squared x. Well, interestingly, I've got a factor here of tangent squared of x that's going to be existing on both sides here. Eventually, I can't divide both sides by that because remember, we're proving that this equality is true. We can't assume that it's true. But let's start here on the right-hand side with tangent squared x, secant squared x minus tangent squared x. And yeah, let's factor out that tangent squared x. So we're just left with secant squared x minus 1. Boy, that looks familiar. That's our friend tangent squared x as well. And tangent squared x times tangent squared x is tangent to the fourth x. So that identity is proven. All right, try this one. Very, very similar to the one that we just did before. Take some time for this one. Well, welcome back. Hopefully that was not all that difficult. Seemed pretty straightforward considering the problem that we had just done prior to this, where we were dealing with not tangent to the third power x, but tangent to the fourth power x. The procedure was in fact very similar. All right, let's take a look at this one here. Cosecant to the fourth x, cotangent x, is equal to cosecant squared x times cotangent x plus cotangent to the third power x. Interestingly, I'm seeing a factor here of cotangent x that perhaps can be factored out of this. That'll leave behind a 1 plus cotangent squared x. I think that'll give us a cosecant squared x. That'll get us a lot closer to this. So, you're going to get to the point here where you'll be able to just take a look at these things and notice, oh, there's a connection between those two things there. Maybe we can make the transition there. Oh, we have to get a common denominator here. Let's break things down into sines and cosines. You'll start to develop a kind of intuition as to which forms of solution turn out to be the best. And so here's what it looks like for this particular problem. If I start with the stuff that's on the right, and look what I'm doing here. I'm factoring out a cotangent x, leaving behind this 1 plus cotangent x. 1 plus cotangent x is just cosecant x. That's one of our Pythagorean theorems there. Identities, I should say. Pythagorean identities. And this can combine with this so that we have cosecant not squared, but cosecant to the fourth x times cotangent x. That proves our identity. All right, so take a look at this one. Very similar problem to the one before. Take some time for this one. Welcome back. Well, if there's anything that these last two problems have illustrated for you, it's don't fear these trigonometric functions when they're raised to high powers here. In the cases that you've seen both times, we're dealing with instances in which you can just factor out, in this case, cosine to the fourth power x, leaving behind just a singular 1 minus cosine squared of x, which can be converted to just sine squared of x. And just recombining everything makes it so our identity is proven. All right, so that's a good discussion on just a lot of the stuff that we've been going through before here. This is a good time now to take a look at some of the strategies that we've been doing beforehand. Think of some of the things that were common. The trigonometric identities, the sine squared plus cosine squared. Sometimes it was in a slightly different form where cosine squared is equal to 1 minus sine squared. We also had these other trigonometric identities, the Pythagorean identities in the same form, different forms. Tangent squared plus 1 equals secant squared. Cotangent squared plus 1 equals cosecant squared. So there's a relationship to watch between tangent squared and secant squared, as well as between cotangent squared and cosecant squared. In addition, if it's not really clear exactly how to proceed, break things down into sines and cosines and see how that goes as well here. So take a look at your activity sheet and go through all of the problems that you did there and see if you can come up with some simple systematic strategies that will work for you in solving these problems, not only in this lecture, but also in the upcoming in-class discussion and the homework problems that you're going to be doing later on. That's it for now. See you soon.